If E and I is not given, then we submit Young's modulus and the area moment of inertia, the axial rigidity equal to 1. But we need this equal to 1 so that we will have some numbers, otherwise everything will be 0. And for units, KSI and inches to the power of 4.
So if it's not clearly stated, we assume that it's 1.
Yes, if it is not given, then this will be 1. If it is given, then we will apply the values that are given. Now, LAB is how much? 20 feet, I think.
Yeah, 240, yeah, in inches.
12 times 20, okay. LBC, I think it is 30.
Yes, sir.
And CD, 30 again.
Yes.
Now, 2EI and 2EI over LAB and 2EI over LBC and 2EI over LCD, they are already calculated. Why is that? Because if you double click, for argument's sake, in cell J4, you will see that there is a calculation there. I have applied this calculation. In the Excel file that you will develop for problem set 10, you will need to apply the corresponding values with respect to the members that you have.
So it would always be like the one that's above it, so...
No, see? I'm sorry for interrupting you, but I will answer your question. We have B4 divided by J3. What is B4? 2EI. 2EI. LCD is J3. LCD. So it is not the one above divided by the one over there. It is the length at the denominator, and at the numerator you have 2EI. Another way to do this, if this confuses you, is what? You can say this is equal to 2 times E times I divided by the length. This is how Excel works.
Oh, it's that little, the block right before it, 2EI divided by LCD.
Yes, exactly. So this value
okay.
came from this calculation. This value is this
Yes.
one. This value is this one.
Okay, thank you.
And then fixed end moment are put in our Excel based on our calculations on our paper.
Hmm?
So what do we have?
0.
Yes, we have 0 for AD and DA. So 0, 0. And we also have 0 for CD and DC.
Yes.
CD and DC. But for BC and CD we have values. So we have equals to 12 times 133.33 and equals to minus 12 times 66.67. Why did I multiply both cells with 12? Here
To convert
and here.
it to inches. Kip
Exactly.
inches.
Pay attention to the unit. Because what the Excel asks from us is keeps inches. What we calculated are keeps feet. And then for psi everything is 0 because this is a no side sway problem.
Because of the roller.
And?
Because of the roller.
Yes.
The constraint.
Exactly. And everything is complete. So be careful. Every line, and this is for problem set 10, because you will need to develop something like this. In problem set 10, I think we'll have a 12 by 12 system. Here we'll have an 8 by 8 system. So we'll have equation 1, 2, 3, 4, 5, blah, blah, blah. Here, and then you will continue your equations. Each equation is developed here. So this equation 1 is what? 1 times MAB. Check your equation 1 that we wrote. And then for MBA, BC, CD, CD, and CD, and DC, everything is 0. So we plug in 0.
Wait, you're plugging in for M, A, B, you're plugging in 1?
Yes, why do we plug 1? Because what we have in the equation, the coefficient of 1, it is 1 times MAB. If you check your equation 1, Gael, you have MAB equals.
Yes.
Your MAB has a factor of 1. 1 times MAB, it's not 0. But for MBA and the remaining, you have nothing. None of those terms are in equation 1. So these are all 0. But your MAB is 1. And then we move theta B to the left-hand side. And this is the calculation. If you double click in cell G10, you will see that this is equal to minus this value. Why minus this value? Because this is the coefficient, this is the term that is multiplied with theta b when we move to the left-hand side. Check your formula. What does your formula 1 say? What do you multiply theta b with?
2ei over L.
See? 2ei over L. When it is on the right-hand side, it is a plus, but when it is moved to the left-hand side, it has a minus. Selby, are you good? Emmanuel? And then theta c and theta d are 0. We do not have these terms in equation 1.
So what are we solving for? Because you said MAB is 1, but then we're solving for MAAB.
What?
Yes, so over here on the right, on the green,
Here?
that's our answer, right?
Yes, this is your answer. You keep inches and you
But
keep
you're
feet.
saying that MAB is 1, so you already solved for it.
You don't solve for it. I didn't say that MAB is 1. These are the coefficients that are multiplied with our terms.
The
Okay.
coefficients from the slope deflection equations?
Exactly. Equation 1 comes from the slope deflection equation. Let me write it down. So equation 1 tells us MAB equals to, I will develop it, okay? 2EI over L AB times theta B, and that's it.
Yes.
You have nothing else in reality. All the other terms are 0. If we move everything to the left-hand side, what do you have? You have MAB minus 2EI over LAB theta B equals 0. Do you all agree with that? Okay. Good. MAB here has a factor of 1. 1 times MAB.
That's this one times one.
This one by L is this one. It is not that MAB is equal to 1.
It's a
In
multiple.
this yellow box, we plug in the coefficients of our unknowns that are multiplied with these terms. So from equation 1, MAB is multiplied with 1. MBA, MBC, etc., they are multiplied with 0 because we do not have them there. Theta B is multiplied with this value over there. And then what you have on the left or the right hand side is the fixed end moment, which in our case is 0. This is the fixed end moment. But in equation 3, your fixed end moment has a value. This is the solution of fixed end moment in equation 3, which remains on our right hand side. This is how Excel works. This is Excel. What we discuss now it comes from Excel. It does not have to do with slope deflection equation. It has to do with solution of matrix problems. This is irrelevant to our course in reality. Okay, so this is how it works. I'm just making this discussion now with you because you will need to plug in some extra equations for problem set 10. Otherwise, you will not be able to solve it. If you decide to continue to use the Excel files, if you decide to use something else, it's up to you. You can even solve it by hand.
So are you saying that that one that you just wrote, if y'all put the numbers that is given right there, I should get that minus 581?
No, this is given if you plug all numbers. These are calculated after you fill this correctly. If you do not fill this number will not come up. Nothing will come up.
Because the green is the matrix, basically, that's what you're saying.
The green, I will double click and then we'll not spend more time there because we need to move forward. This is an Excel command that gives you the solution. But if it might give you an error, it has to be a 9 by, here for example, we have an 8 by 8 problem. If it is not an 8 by 8 problem, or an X by X problem, Excel will give you an error, will not give you a solution. So you also have the command. There are 2, 3, 4 minute videos in YouTube. This is how I didn't know this. When I learned about this. I don't remember this from the top of my head. And I do not expect you to remember this from the top of your head. That is the reason I'm providing this to you. I could let you spend half an hour, 1 hour to watching YouTube and learn how to generate it by yourselves. it's okay, but you will learn nothing. But you need to develop it. Okay? You need to move on from here. Questions?
The reason why those are X'd out is pertaining just to this problem.
Yes, exactly.
Okay.
Because MDC is equal to 0. Our last equation, Kimia, is MDC equal to 0.
So in problem 10, we can use this sheet, or do we have to kind of make our own?
You can use
Because
this,
this is
but you have to adjust this.
Okay, because we have a 12 instead of
I think it is a 12 by 12. I
Okay.
think. I don't remember. So you need to add some extra
Yeah.
2EI over L, some more fixed end moments. You will see that your psi will not be 0.
Yeah, there would be like a DE and a DF. Yeah.
Now, eventually, before we move on to the next, first of all, are there any questions here? In slope deflection method, not in Excel.
No.
Dylan?
Hold on.
No?
Hold on.
Now, why do we need these? Because we use these values. What do we use them? This is problem 1. No, this is not problem 1, this is problem 2. To develop this is the free body diagram of what we have. And this is what I want from you to develop for the solution of problem set 10. Because one of your questions is to give me the free body diagram. This is what I want to see. Of course, you will have three columns instead of 2, and at the bottom you should have also fixed, pin, fixed. How do we start? MAD equals to minus 48, 48. See what we have down here. MAD, 48, 48.
You following the device?
Excuse me?
Are you following the device?
Actually, this minus tells us that this is the analyst convention. So this goes clockwise. See? This goes clockwise. MBA is minus 96.97. Minus 96.97. We have it here. Actually, this is where we apply it, and then this is the opposite over here.
Why do we apply it there? Why didn't we apply it over here or like up there? Is there like a reason, or do we just apply it there just to say?
This is a good question. I will respond, but give me 1 second. No, I was mistaken, Selby. This is where we apply it, and this goes clockwise. That is why it is negative. But to answer to you why we apply it here, because this is your member AB. Over here you have your joint B. So the value is the same, but it is opposite. We isolate our members, and this is where we apply the values that we find. And then based on the values that we apply the opposite direction to the nodes, to the joints.
Okay.
Okay? Did I answer your question?
Yeah, because that's like where the member.
So we
AB
isolate the
ends.
members, the column in that case, or the beam, which is where we apply the correct orientation, and then the opposite orientation goes to the joints.
Okay.
And of course, here you have clockwise. At the fixed effect, support, you will have a counterclockwise moment. Now we have all the moments that we apply to our members. Here what we have a 0 here, so we have nothing. Okay? And which is normal because MDC was a pin, if I'm not mistaken.
Yes.
So we apply this, and then we use equilibrium to calculate the shear forces and the axial forces. This is how you solve it. What you find from slope deflection equation are the blue values. And then from the blue values, by applying equilibrium, you can calculate all the red values. And I have these calculations in the handout that I uploaded on Canvas. So you can find the calculations for this on Canvas. These are the calculations for problem set 1, from a study guide problem 1. And here we have the calculations from study guide problem set 2. Wait, no, I don't have it. Yes, I don't have the equilibrium. Okay, any questions before we proceed? This is what, write it down. This is what I need to see for free body diagram in part 3 of problem set 10. This is on Canvas.
So, you broke it there to represent it being broken at the joint, not Because to me, you're breaking it in the middle of the beam, but it's supposed to be like you're just showing it.
It's not in the middle. Yes, in reality, you break it like
If it was there
over here.
on
let's say.
either side.
Yes,
Oh, okay.
but we zoom in so that we can draw them.
Yeah,
Otherwise, we
okay.
wouldn't be able to do it. It is not that here you have 1 foot, let's say.
Yeah. Okay.
Yes, Gael?
I think I saw, but it's another one. We had the two load on top and then the wing. So we delete those because we're only doing internal ones.
You can have the the uniform distribute load and the point load, but you can have them higher up.
They're
Doesn't matter.
they don't matter really. 'Cause
They matter. In the free body diagram, you should have the externally applied loads. In the free body diagram, you should have externally applied loads, support reactions, the forces at the supports, dimensions, and these loads. All must be included. So, in reality, this is not a completed free body diagram because the supports are missing and the externally applied loads are missing. So I lose 30% of my points.
Wow.
The red numbers, you calculated those from equilibrium?
Yes. You isolate the members and the joints and you solve with equilibrium.
But the exterior doesn't matter when you calculate those.
Yes, because exteriors we use them to calculate the blue values. So the exteriors are included in the blue values. If you add them again, it will be another problem. In your equations, I mean, not in the diagram. In the diagram, you can add them.
In this PDF on Canvas, did you show how to solve for the red ones?
No, I don't think. But if you need it, I can spend some time and show it to you. Is it something that you would like to see?
More than likely, yes.
Okay. You will have it before Thursday. Are you good to move on to the last part of midterm exam 2? Let us see what we have. Today, we will work
And our exam is on Tuesday, right?
Tuesday, yes. Today, we will focus on solving frames that can sway. This is our problem. What do we have here? We have a frame which externally has 2 point loads, one horizontal, one vertical, of 10 kips and 20 kips respectively, and one uniformly distributed load that acts on the beam of 1 kips per foot. You have the lengths of both columns and of the beam, and you have a fixed support at joint A and a pin support at joint D, and the problem asks from us to provide the free body diagram, the shear forces and bending moment diagrams. Why this is not, which is the reason for which this is not a no side sway frame?
Because it's a pin and
No.
a fixed. Pin and fixed.
There's no roller at this time. What did the roller do in our previous case?
Give us the direction, the movement to the horizontal.
Say it loud, Selby.
It gave us the horizontal movement, right? Or
It prohibited
prohibited that one.
horizontal movement. So it was constrained.
Mm-hmm.
So it could not move, and additionally, this is not symmetric. Remember, if it is symmetric in terms of loading, geometry, and flexibility, then again this is a no side sway frame. But it's not the case here. So this is a side sway frame. Let us see the difference. We start as we started in our previous case. Step 1. Which is step 1?
Identify DOS.
Very good, Kimia. I, D, O, Fs. What degrees of freedom do we have here? Jocelyn, which is the maximum number of degrees of freedom we could have? The maximum number. Something easier. One joint in a 2D system, how many degrees of freedom can have?
Is it
Something else for you. What is a degree of freedom system? What is a degree of freedom, not system? What is a degree of freedom? Is it a force? Is it a displacement? What is it?
is the displacement, right?
Okay. And rotations.
And rotation.
Yeah. So you have a 2D system. So how many translations and rotations we can have?
For A,
For A, for example.
3,
3. Which are the 3 that we can have?
the rotation, the one that goes up and to the actual.
Good. So now you have 4 joints. How many degrees of freedom we can have in total?
See that I don't understand. That the
One
entire
joint,
thing-
okay, one joint will give you 3 degrees of freedom. So 2 joints, how many degrees of freedom will give you?
Um,
3. Here, how many degrees of freedom do you have?
do you count all the forces that go up and down?
Not forces,
Not.
translations and rotations. Degrees of freedom are translations and rotations. They are not forces. They are movements. So here you can have 3 movements, which you said very correctly. Here, how many movements you can have? I'm not saying that even the prohibited ones.
So what do you mean?
No. Here in reality you have no movement, but because it is a joint, you can have 3, ideally. Here, how many you can have?
So I don't know.
3 again.
But that's because it translates from A to the. to
No,
the
no. We say that this joint can go up and down, left or right, and it can rotate. We don't know if it is prohibited.
Yeah, that's what I meant, like the forces that
Yes.
go up.
Not forces, displacement.
Sorry, displacement, not force.
Yes. So you can have 3 here, same here. So you can have 12 in total. This is the maximum number of degrees of freedom that we can have. Let us go and see if some of them are excluded. So here we have a fixed support. Can this joint move or rotate? Translate or rotate, not move. No, it cannot move, it cannot translate. So 3 degrees of freedom go away from here. At joint D, this is a pin connection. It cannot go up, down, it cannot go left or right, but it can rotate. This is 1 degree of freedom. Theta D, write it down.
What should I call this lesson?
This lesson, slope deflection 3 frames. Now, let's go to joint B. Jocelyn, can joint B go up and down? What's that? It doesn't matter if you don't answer correctly. It doesn't matter.
I think no,
Why do you think no?
because it's attached to the joint A and C.
Exactly. Joint A, not C.
Oh, sorry.
Here you have a fixed support. So fixed support prohibits A, B to go up and down.
Mhm.
So B cannot go up and down. Can it rotate? It can. Nothing prohibits it from rotating. So theta B, write it down, is another degree of freedom. We leave the horizontal movement for now. Yes, Jocelyn.
So essentially what we're doing is we're writing anything that can rotate, any of the joints that can rotate.
Or translate. We will see. For now, we saw that A can do nothing. D can rotate. B can rotate. We have not considered the horizontal movement yet. We will see that. And let's go to C. Can it go up and down? Why no, Corbin? Exactly. The pin does not allow joint C to go up and down. It keeps it there. But it can rotate. So write it down. Theta C, another degree of freedom. And now let's go to delta B and delta C. Delta X B, delta B comma X, and delta C comma X. Can it go? Can these 2 joints move horizontally?
Can you repeat the question?
Can joints B and C move horizontally? Yes, they can. There is nothing to prohibit them. And of course, this is not a symmetric system. So this is a side sway system. In reality, it can go like this. So joints B and C, they can move. Now, the question is this movement the same or not? Can delta C translate more horizontally than B? No, it cannot extend or contract. It might be under tension or under compression, but it cannot become bigger or smaller. The length remains the same. So delta B x is equal to delta C x. And this is another degree of freedom. So you have theta B, theta C, theta D, and delta B x equals to delta C x equals to delta. So now we have 4 degrees of freedom. And on top, what is different from what we solved last time, that now we have a translation instead of considering only rotations.
Professor, can you explain one more time why delta B and delta C are the same?
We know that horizontally it can move, but we also know that a beam cannot extend or contract. It can, but it is not given here. Maybe it is given in some cases, but in this case this is not given. Since this is not given, we assume that the length remains the same. So since your run before BC is the same, the before BC distance will be the same. So if it moves by delta, this must move by delta, so that the length will remain the same. Other questions?
Just to be clear, that's a degree of freedom because there's no supports and it can technically move, but because they're the same, we just equal it to
Yes. Exactly.
delta.
It is a degree of freedom because nothing constrains them,
Okay.
as you said, and they are both equal because we're not given that one of the two has different displacement than the other. So the length must remain the same.
Okay.
Now, step 2. You know step 2.
Slope deflection equation.
Very good. Do you all agree with this? It is the exact same problem, geometrically. So you have the 6 equations, MAB, MBA, MBC, MCB, MCD, MDC. These are your 6 equations. Now, how many are our unknowns in this case?
It'll be 9 again
Why 9?
because we have the 6 equations and the 3 unknowns.
How
from
many are
each.
the unknowns? Are they 3?
Well, we don't have roller anymore, so.
Oh, we're right.
You have 4 plus this one. So
Oh,
now you have-
including that one, not 5.
No, yes, because these two are the same. So this is delta.
So you
Okay.
just consider as
And then eventually the value of delta will be the same value for delta C and delta B.
So we consider it 1 and not separately 1.
Exactly, this is one.
What about the fork? If that would be
The
a
fork is psi.
yeah. Outside. Outside.
Psi.
Psi.
PSI. PSI.
That'll be an unknown as well.
Of course, no. This is not an unknown. This is an unknown because it involves delta. Your delta is your unknown. It is not your psi.
Alright.
Your delta is your unknown. Yes, Trace.
So on BX and CX, it would create 2 unknowns if they didn't equal deflection.
Exactly. So instead of 4, you would have 5. So now you have 6 equations, 10 unknowns. Now here we are stuck. not give up. We will go to step 3. What do you know? Which is step 3?
The FNM.
Fixed term moment, and what Gael likes, size.
Works.
So you have 6 minutes to write down fixed term moment and size for our cases.